Hi, this is a supplementary physics lesson on chapter sections 19.4 and 19.5 in your textbook, covering electrical potential. And we have discussed previously the comparisons between the gravitational force in our universe and the electrostatic, or well, we can even say the electromagnetic force in our universe. We've seen that as far as the amount of gravity, the force of gravity between two masses are as expressed by Newton's law of universal gravitation, depends upon the two masses involved and the distance between them, okay, the gravitational force. We also have seen through Coulomb's law that the electrical force between two bodies, two charged bodies, has that same exact relationship. It depends upon the amount of charge of the two objects in question and the distance between them. Okay, and so this concept of electrical potential, in other words, since it is a force, since the electricity charged objects create a force on each other, just like objects with mass create a gravitational force between them, okay, that force between them is what causes the potential to do work, okay? And so we've discussed in our sections in gravity, if we have the Earth here represented by that circle with a mass of a known mass, and we have a satellite orbiting the Earth, okay, we have said, and we have done problems with this, if this satellite is in a particular circular orbit and it moves from this point here over to a point here, okay, the same distance above the Earth's surface, it's just moved in orbit to another location above the Earth. The work done on that satellite by the force of gravity is zero, okay, because it still remains the same distance above the surface, okay? We've analyzed that down here on Earth. If we have a baseball and we throw a baseball perfectly horizontal to the surface of the Earth, H has not changed. Okay, we say gravity has done no work on that object. Okay, it has not gotten closer to the Earth. It has not gotten farther away from the Earth. It's the same potential. Okay, it's the and remember, the potential energy due to gravity depended only upon the height above the surface. The same concept with electrostatic charges. Okay, if we have a massively charged object here, a positive, and we have our positive test charge here, if we move, and these vectors here represent the electric field, okay, which also represents the direction of the force vector away from that massively charged object, okay? They go radially outward. If we take our test charge and move it in a perfectly circular fashion over here on this side of the charge, okay, how much work has been done on our test charge due to the electrostatic force? Well, it's the same analogy as with gravity. It is the same distance away from the massively charged object. It's just in a different location. Okay? So the net force, the net work done on that is zero. Okay? The electrostatic force has not done any work on it. It only does work if it does work in the direction of that force vector. Remember way back from our definition of work is this as a force times a distance, okay? And we say for there to be positive work, and when more appropriately, you know, remember we said it's actually the cosine of the angle times the distance of the cosine of that angle between these two vectors, okay? And so if the force, in the case here, an analogy to throwing the baseball across the surface of the earth, if we have a charged plate, okay, a flat plate, like we had the flat earth up here, the flat plate, the vectors, the field vectors proceed outward from that positive plate radially, okay? If we have that positive test charge and we move it from this location to this location, there is no work done on that, okay? Why? Because the displacement of that test charge is perpendicular to the force vectors. Therefore, this cosine term goes to 0. The cosine of 90 degrees is 0, okay? No work done on that. It's the same concept as with gravity, okay? So just as with gravity, we had gravity, potential gravity. We had the potential of gravity to do work. We have the potential, okay, for an electric charge to do work, okay? And that potential we give the name volts to, okay? Volts, electric, potential, electrical potential here, okay? It's in the SI units of joules per coulomb, okay? We have two equations in the book in section 19.4. I would say peruse over that section quickly. It gives some derivation as to how they are so similar between gravity and electrical. That's a little too far in the weeds to get with this remote learning thing. So I would say peruse that section. These are the equations you need to know to do your homework tonight. Okay, those two indicated in the book. And remember, our electrical potential, okay, is expressed in terms of potential energy per unit charge, just like our field strength was expressed in force, electrical force per unit charge, okay? And then we have another equation here for potential energy, okay, based on the distance relationship. So again, the clue in, if they don't give us a distance in our electrical charge problems, okay, that means we're going to go to this one, and that distance information will clue us into which equation to use, okay? So I just wanted to show you those comparisons, the analogy, and how and why. Because both of them, fundamental forces in the universe, gravity and electrical charge, okay? Both of them central forces. Both of them conservative forces, okay? Both of them act based on between objects based on the magnitude of the proper variable involved. In the case of gravity, it's mass. In the case of electricity, it's electrical charge. And it has to involve the square of the distance between the two. So just to go over a couple of your questions, homework questions, to give you some pointers. So I'm giving you section 19A, question number 4 and question number 9. Both are basically asking the same thing. And I would refer to, although I would ask you to peruse section 19.4, I would ask you to read with understanding section 19.5 and pay particular attention to these drawings they have of electrical fields with those lines of equal potential drawn. And so when I say equal potential, well, I say if we move this test charge from here to here, the distance from the plate to the test charge is the same at all points. So the electrical potential, the potential of this electrical charge to do work on our test charge, is the same at all points. Okay, what is it wanting to do if we let it go? It's wanting to push that positive just charge away, because like charges repel. Okay, so it's wanting to push it away. It's wanting to push it away the same amount here, as here, as here, and as here. And as we notice, that line of equal potential is perpendicular to the field lines at all points. Over here, we draw that equal potential line, and this is just an imaginary line, you know, saying at that point, it is perpendicular to each radial vector that I've drawn here, okay? And they have that picture. They have a picture of it with this plate. They have a picture of it with a single massive charge. They have a drawing between two massive charges, okay, where the lines of equal potential, I would say, are kind of potato shaped. And then they have one that's really irregularly shaped, okay? But the clue in is if the test charge moves anywhere along this imaginary line of equal potential, there is no work that's been done. Okay, it's the same distance away from the charged object. Okay, whether it's from here to here, or whether it's from here to here, or to here, or to there. Okay, so look at those drawings. I would read over section 19.5 maybe twice and read over it carefully, where the other one, 19.4, just peruse it. Okay, so question 6 on the chapter review. What they're actually asking you to do there is to draw 3 sets of charges 3 centimeters away. One, they'll be positive, positive. One, they'll be positive, negative. Oops. And one of them, they'll be negative, negative. And they want you to draw the force lines, the electric field lines, and a line of equal potential around those. And they actually, if you look at those schematics on section 19.5 on page 418 of your textbook, they already give you what one of those will look like for the positive, positive. And then also, I think we had one of those previously. If you look back on page 415, they'll give you what those electric field lines will look like for a positive, negative. Okay, and then you have to draw in some lines of equal electrical potential around each of those. Okay, so you'll have 3 answers to your problem. That's what's the setup for that one. On questions 32 and 33 in the chapter review, you're going to be using these 2 equations to determine the electrical potential for those questions, and I'll just give you a clue. Okay, one question you'll use one of the equations, and the other question you use the other of these 2 equations. So you'll have to determine, based on the given information, which one you'll use. So I hope that helps with your homework assignments, and I just wanted to compare the similarities between gravity and electromagnetism in our universe. It's really an amazing comparison, and it's another testimony, okay, that we have an intelligent creator that created these things. To imagine these comparisons came out of random happenstance is really beyond belief to think of that. So I hope that helps with today's homework. Shoot an email or a text message with any questions. Bye for now.